SAR Image Formation. SAR experiments were conducted using the Fmcw radar described in Section 2. An experimental diagram is shown in. The experiment was conducted inside an anechoic chamber with a maximum range of 7 meters. The broadside-facing radar was placed on a rail moving in a cross-range direction to the target. The total synthetic length was 2 meters and the target was in a range of 2.8 meters. The target was a trihedral corner reflector. Depicts the experimental settings, which assumed a non-squint radar geometry and that the antenna was oriented perpendicular to the track direction during motion. The rail motion was controlled by a motor. As shown in, the radar platform moved along the rail. Because its flying speed was low, the interval on the rail was set to 0.001 meters. The total number of measurements was 2001. Diagram of SAR experiment settings. Configuration of experimental settings. The transmitted signal was scattered by the target. The nth received signal from the impulse target after IFFT was SRN and is written as 11. As shown in 2, the phase delayed received signal can be represented. Herein, Re refers to the distance between the antenna and the target, and I refers to the ith scattering coefficient and antenna pattern with respect to the observation angle. In addition, PF refers to the impulse response without a delay and lambda refers to the signal wavelength. The range profiles of all 2001 measurements are shown in. A single range profile at the center of the synthetic aperture is shown in. The target signal is visible at a range of 2.8 meters. Such range profiles can be stacked with regard to the antenna position to form a two-dimensional range profile, which is shown in. As the figure illustrates, a frequency of 94 GHz and a narrow beam width of approximately 10 degrees were used. The target with a relatively short distance was measured. Range profile of the impulse target. Measured range profile in 2 dimensions. The difference between the bore sight range and the antenna of 3 dB edge sight range can be represented as 12. The range cell migration can be neglected because the difference is sufficiently less than the range resolution. The target signal phase changes with respect to the antenna position. From the phase history of the point target located at x0 and y0 can be derived as 13. The azimuth compression can be performed by using 13 to create a matched filter along the cross-range direction. Since the curvature of phase n, 12, varies with range, a different azimuth matched filter must vary with the range. Shows the azimuth compression filter. The SAR image is obtained through the azimuth compression, as shown in 13. The process of obtaining the SAR image using the Fmcw radar is shown in the flowchart in. Flow diagram of SAR imaging. In the W-band, RCM does not have to be used depending on the range and the antenna beam width. After applying the azimuth compression filter to the two-dimensional range profile, the azimuth compressed SAR image of the impulse target is obtained, as shown in figures 14 and 15. Azimuth compression filter. Azimuth compressed SAR image. Azimuth compressed SAR image shown in 3 dimensions. The range profile in the SAR image can be represented in figures 16 and 17. The range resolution of the SAR image is lower than the impulse range response shown in. This degradation is estimated to be due to azimuth compression and may be improved via a precise range cell migration. Range profile in SAR image. Point target profile in SAR image. The cross-range profile at a target range can be obtained by taking a column from the SAR image. This profile with the target location is shown in. Cross-range profile of the impulse target. A detailed analysis of the point target is shown in, including the side lobe level and resolution. The theoretical null-to-null cross-range resolution of the SAR image can be calculated using 14. Detailed analysis on the cross-range profile of the impulse target. Because the target range is small, the synthetic length is governed not by the antenna position but by the antenna beam width. The 3 dB beam width of the antenna, that is, 10 degrees, was used for the calculation. Table 2 outlines the resolution in the cross-range direction. The cross-range null-to-null resolution is 0.0183 meters, and the cross-range half-power resolution, 3 decibels, is 0.0076 meters, as measured by the SAR experiment using the impulse target, as shown in. The experimental null-to-null resolution matches the theoretical expectation of 0.0183 meters from 15. Measured cross-range resolution of SAR. An experiment was conducted in which three corner reflectors 0.06 meters apart from each other were placed at a range of 2.8 meters. The target settings are shown in. Experimental settings of multiple targets. By using the same processing in section 3.3, a SAR image of multiple targets was obtained. The range profile for the three corner reflectors is shown in. Using the Azimuth Compression method in section 3.3, the SAR images were obtained. The SAR image is shown in, where its magnitude is in the decibel scale. The three-dimensional SAR image is shown in. The positions of the corner reflectors are approximately 0.06 meters apart in the cross-range direction. The targets are located close to the cross-range direction, nevertheless, they are clearly distinguishable. Any arbitrary object can acquire SAR images using the above SAR focusing method. This SAR imaging method is very simple, however, it is a powerful method for acquiring real-time SAR images. Measured range profile for three corner reflectors. SAR image of multiple targets. Azimuth compressed SAR image of the multiple targets shown in 3 dimensions.